Hello, community. Stable diffusion. What are the insights and what are my answers? A lot of you ask me, so what are your answers? Okay, if you want to know, here we go. Now, last video showed you that the most advanced text-to-image AI system, Stable Diffusion, as of September 2022, fails to draw a single letter A and fails to draw a single square in a two-dimensional space on a two-dimensional canvas. And you might ask, why is it? It can create such beautiful pictures you see every day right now on the internet, but why is it not able to perform the most simple tasks? Let's have a look at this. You might start with the following idea, or what you've noticed is, maybe the system has not been trained on a text-image pair that shows simply single letters or simple geometric forms like a square, like a circle, a sphere, a planetoid, whatever. Now, if this is the case, then it would be just a problem under parentheses of the training data set. Then you would just show the system simple pictures of the character A, the image A, and you write in the text, this is the letter A. So if this would be it, there would be an easy solution for this. But you know, there's something else. The system doesn't know what to do if you write in the text a 2. Either it paints it as a sign 2, or sometimes it writes the word 2, this 3-character word 2, and I have the feeling the system doesn't know if I provide some text that it wants the visual image of this or the written image of this. It's interesting. I think there could be a missing link in the cross-attention. This language image tuples, they kind of dissolve at a certain level in latent space. But you can improve cross-attention, of course. So also we could improve this specific problem. But then we think about the whole system and imagine, it is not that we, when we were young, we were learning single letters, single numbers, forming words, adding words together to a sentence. If you already start with terabytes of RAM available, maybe a system that is trained on all these two-dimensional images and text tuples, maybe the system forms its own alphabet and its own numbering system. And maybe the internal representation in the latent space, in the low-dimensional latent space of the image tokens, are non-human signs. I don't know. It is an idea that I have. And maybe the training on what is an apple to us and of its component might have induced novel solution in this terabyte of RAM that is analyzing millions of examples of text image tuples. If you generalize this idea, you might say the human visual code and the human language code in particular, our sentences, our words, may not be the most compressed, efficient semantic form to describe an object, to describe a situation. And the training on our semantic tuples that we provide in a two-dimensional plane as an image and a text accompanying the image tuple might induce in a supercomputer a novel semantic configuration space, what we also call the representation space or the latent space or hidden space or whatever you might like to call this, if you think about the schematic algorithm of stable diffusion or of LDMs, of latent diffusion models. And this is not unfamiliar to us. Think about an apple. You can describe an apple by its outer form and texture. More or less it's round, it has maybe the color of yellow, the color of green or of red. The texture of an apple has a specific quantity. Or we as human, we have an understanding that an apple is topological close to other forms. An apple grows on trees, so apple and trees. And if I go to a tree and I pick an apple with my hand, I have apple in my hand. And then I take the apple and I put it here on the table in the kitchen. And you see the apple is in familiar forms for us as human beings. But you can also watch an apple if you have a cross-cut analysis of its chemical components. You have a chemical component structure analysis. Or you just go by its reflective and non-reflective behavior of the surface. We don't know how a supercomputer will react to these specific details, visual details. You can think of an apple, and we do this in fluid dynamic systems. How much water does an apple need when the apple grows? What about cell differentiation? What is the task of specific cells in the apple? How does fluids flow in an apple? How does water is provided, nutrition from the ground? What about density gradient distribution within the specific objects? So you see, we have so many abstractions that we can work with. So I would not be amazed if a supercomputer comes up with a different classification system. But you know, there's an interesting question if you reflect on all of this. Because the main question is, what was learned by the system given its specific diffusion model architecture? And if you compare this to humans, we all learn the same in school. We start with the alphabet, A, B, C with the letters, maybe we have the numbers 0, 1, 2, 3. And then we communicate and we build longer sentences, more complex sentences. We communicate, we interact, we learn, we are part. We are part of the society in this 3-dimensional, 4-dimensional society. Now, if you provide a supercomputer just 2-dimensional images, a 2D plane, and you do not separate in time, because all those pictures are provided without a time index. So a supercomputer just learns on 2-dimensional images with no specific time differentiation. I think it's highly interesting from a mathematical point of view. How does the system discriminate objects? A computer cannot understand that when an apple is small, where it is, what happened, what can happen to an apple, what cannot happen to an apple. You know, how does a computer analyze it and discriminate it image tokens in a diffusion system? Can it discover new symmetries that are somewhere hidden deep inside the code? I think these are interesting and fascinating questions. So we as humans, we can learn quite a lot trying to understand our computer systems, how they work and why they come to the results, and what are their limitations. And this is one of my driving forces when I take a new system and I say, hey, draw me a circle, write a letter A. I start with the most simple form to understand what are the capabilities of the system. It's nice to play around and create something funny, of course. But you know, we want to advance our knowledge and we want to, I don't know, maybe discover new symmetries, build upon something that maybe the position of an outside observer. We live in this 3D world, you know, but a computer is behind a glass screen and he only sees non-time discriminated 2-dimensional pictures of the world. And the computer tries to make sense of this all. I think it's a highly fascinating topic. If you have some ideas, leave me a comment in the description of this video. And if not, I see you in the next video.